Newton and Einstein are two of the most influential figures in the history of physics. Their work revolutionized our understanding of the laws that govern the physical world. Let's take a journey through their contributions to the field of physics and see how their ideas transformed our understanding of the universe. Newton's laws of motion. Sir Isaac Newton, a physicist and mathematician, laid the foundation for classical mechanics with his three laws of motion, published in his work, Philosophiae Naturalis Principia Mathematica, in 1687. Newton's laws are as follows. A. First law, law of inertia. An object at rest will remain at rest, and an object in motion will continue to move at a constant velocity unless acted upon by an external force. B. Second law, law of acceleration. The rate of change of momentum of an object is directly proportional to the applied force and takes place in the direction in which the force acts. C. Third law, law of action and reaction. For every action, there is an equal and opposite reaction. Newton's laws provided a comprehensive framework for understanding the motion of objects on Earth and in the heavens. They formed the basis of classical mechanics and were used to explain planetary motion and the behavior of everyday objects. The theory of gravitation. One of Newton's most significant contributions was his theory of universal gravitation. In 1687, he proposed that every particle in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. Newton's law of universal gravitation mathematically described the force that governs the motion of celestial bodies, such as planets, moons, and comets. It provided a unified explanation for the motion of objects on Earth and in space. Special theory of relativity. In the early 20th century, Albert Einstein revolutionized physics with his theory of special relativity, published in 1905. Einstein's theory challenged the classical notions of space, time, and motion and introduced new concepts. A. The principle of constancy of the speed of light. Einstein postulated that the speed of light in a vacuum is constant and is independent of the motion of the source or the observer. B. Time dilation. According to special relativity, time is not absolute but is relative to the observer's motion. Moving clocks tick slower relative to stationary clocks. C. Length contraction. Objects in motion appear shorter along their direction of motion as observed by a stationary observer. D. Mass-energy equivalence. Einstein's famous equation E equals mc squared showed that mass and energy are interchangeable, and a small amount of mass can be converted into a large amount of energy. Einstein's theory of special relativity provided a new framework for understanding space, time, and motion in the universe, especially at high speeds or in the presence of strong gravitational fields. General theory of relativity. Building upon his special theory of relativity, Einstein developed the general theory of relativity in 1915. It extended the principles of special relativity to include gravity and introduced the concept of curved spacetime. According to general relativity, mass and energy curve the fabric of spacetime, and objects move along the curves created by massive bodies. The theory explained gravity as the curvature of spacetime rather than a force acting at a distance. General relativity made several successful predictions, including the bending of light around massive objects and the existence of black holes. It provided a new understanding of the structure and evolution of the universe on the largest scales. In summary, Newton's laws of motion and theory of universal gravitation laid the foundation for classical mechanics, while Einstein's theories of special and general relativity expanded our understanding of space, time, and motion, especially in extreme conditions. Their contributions to physics transformed our perception of the physical world and remain fundamental pillars of modern physics.